write down real quick as a reminder because it's important. This gets lost in everything. Okay, I tried to start Arrhenius the other day, but I didn't do very good, so I'm going to pick it up again. But the whole point, when we were talking about rate laws and integrated rate laws, whatever data we were looking at, whatever equation we were using, it always happened at one particular temperature, because that's the way you find the rate. You have to keep the temperature constant, because the rate constant is going to change when you change the temperature. You heat something up, things move around faster, there's more collisions per second, and it speeds things up. So, but I want to talk about Arrhenius today. First, let me show you. I finally got a little bit of the kinetic stuff on here. Now, I've got integrated rate law. This is just about state rate law. There's no calculations in this one. I keep trying to get more on here, but I feel like I might push the test to Wednesday next week. Not next week, but following week. Just because I've been stumbling around trying to explain this stuff, and I'm not doing great. But we'll start with this today. And Arrhenius equation. One other thing to show you, I want to get you up. Home screen. Test 1 equations. So I've got these sheets, like I just gave you the Arrhenius sheet for this. There's also this sheet that I gave you the other day. Those I'll give you on the test. You don't have to memorize them, just be able to use them. Solve them. Arrhenius. So I'm going to just go through some of these. The Arrhenius equation is rate constant equals a exponential, and it's negative activation energy, constant R, temperature. Temp has to be in Kelvin for this. that's activation energy. It'll always be in joules per mole for the calculations we do. R is 8.314 joules per mole Kelvin. Temperature Kelvin. It's supposed to be an ugly K. What else? E equals you don't really need to know this. It's 2.7. I forget whatever. It's like pi. It's one of those sort of transcendental numbers. But we use a calculator for that, so you don't really need that value. A is called the frequency factor. That's just a vocabulary word. We won't. Where the frequency factor comes from is pretty nebulous. Okay. All right, let's leave that there. And then this kind of goes. This is. This is more related to rates than Arrhenius, but I wanted to bring it up. Number 56. No, I guess it goes in here because it's temperature. Rate for a reaction doubles for every 10 degrees C rise. How much faster does the reaction go at 45 degrees C versus 25 degrees C? So for every 10, so if you're at 25, 35 to 45, you jump 10 degrees C twice. So for each one of those, it doubles. So if you double from here to here, that's times 2. And then you double again here, so it's times 2 times 2. So to get all the way over here, I just wanted to show you this simple math. For each time it doubles, it's 2 to the and it works the same way with triple. So it's 2, and you got 2 of these intervals from 25 to 45, so it goes 4 times as fast. Does that make sense? It doubles, and then whatever you got after you double it again, and that's 2 to the second power. Makes sense? Double and then double again. That's 2 times 2. It's not 2 plus 2 is what I'm getting. You with me? The next one says, this is an easy question to put on the test. So. How much faster if it's 95 to 25? So now we're going 25, 35, 45, 55, 65, 75, 85 to 95. We do it 1, 2, 3, 4, 7 times. So to do that, if it doubles, you put a 2, and if it does it 7 times, you put a 7. Do you know what that is?
128.
Yep. You computer guy? Or you just do that? Because computer is binary, that's why memory allocations and stuff are always in powers of 2. So yeah, 128. You just do it in your head. He's got his calculator sitting on. All right. So I just wanted to throw that in there. But since this is rate versus temperature, this is why we're in this chapter, Arrhenius. But you didn't need the Arrhenius equation.
How did you do A again?
A went from 25 to 45. So for every 10 degrees C in temp, you double. And there's a 10 degree temp and there's a 10 degree temp. That went 2 times. So that was 2, 2, 2. So that one was 4x. And this one was 128x. If it tripled every 10 degrees C, then I would have a 3 here. Then I would have a 3 here. You see what I mean? I still think I'm short on questions on D2. I definitely am, but even for trying to get caught up, what I managed to get on there yesterday still didn't. And I probably can't get back to it till Sunday, so. If I can't get everything ready like mid next week, then I'm definitely going to push the test forward. So, because I've got to show you how these things are going to look on the test, because I know I've been kind of scattered. Okay, again, the chapter, and this is number 58. For, I'll just say, decomp reaction, or some decomposition reaction. And they give you the reaction, but it doesn't matter. The rate constant is second. I'll just list things. That's the rate constant. They tell you that activation energy is 261 kilojoules per mole. And I'll say and I will give you this on the test. This shows up in a few of our equations. That's that gas constant. So I'll go ahead and write it here. Mole Kelvin. And so you've got, oh, and then you're asked, well, what is the, that's what you're asked for. So you're just going to use this equation. A question like this, you're just using that equation. But it's a little tricky because of the E, so I'll show you how to do this on the calculator. I figured out how to do it on these calculators, so that's what I'll explain to you. If you practice at home on your own calculator, you need to figure out how to do it. Before I continue, this is what we're looking for. First, look at these units. I told you that, I should have erased it. Energy of activation is in joules per mole. T is in Kelvin. R is joules per Kelvin, but I'm just going to give you that one, so you'll have the right one for that. They've given us K is in this doesn't really matter, but when you see this, does it tell you anything? If that's the unit on K, what does it tell you? It tells you the order. If you don't remember which order that is, then
Zero.
that's this one's first order. So if X is 1, then this becomes 0. If X is 1, this becomes 0, so those go away. So it's first order. But that doesn't matter for this anyway. But notice, we've got this in degree C, so we have to turn that into K. 325 plus 273.15. 598.15. Really, I shouldn't have the 0.15, but since I'm not done with the calculation, I'm going to leave it there. So temperature is really okay, and there's another one. This is in kilojoules, and we need to be in joules because everything over there is in joules. So this I would turn into 261,000 joules per mole. And now I think I'm ready. It's just a matter of doing the calculation. This is joules per mole. R is joule per mole Kelvin. T is Kelvin. You end up with no units. All the units cancel up here in the exponential part. So once you calculate this with E, you've got no units. The units are gone. So A, you can easily tell what the units will be on A because they have to be the same units that are on K. So A is going to be in S negative 1. So two things, check your units, make sure you're right. B, if you're solving for this, you're solving for A, no units come from here, but you do end up with a unit that comes from here. All right, I would start with your RT. It's negative. Energy of activation is 261,000. I'm going to leave the units off. R 8.314. Temperature is 598. Really, this is three significant figures. This is 4. This should be 3. I'm just keeping the 1 5 for round off error. On a test, none of the answers are going to be anywhere close to each other. So if you're a little bit off from an answer I got there, you just know we're off by a little bit. So you'll still know which the answer is. You follow me? So if we solve that, I pre-solved everything today. We get I have a note if you're looking at the PowerPoint on how to solve for these on this calculator. It turns out what you do is you go you hit second. I put this on the PowerPoint. I wasn't thinking, but your calculator might say inverse. And then you're going to hit that, and then hit that, and then inverse that. Then hit that, and then type in negative 52.5 bottom, probably 2.5, and then hit enter. And you should see 1.58 change 10 to the negative 23. And that's what we're getting out of this. So learn how to do that on your calculator for practice. I think I have to make you use these calculators for the test though. But that's what you get for this. So now you have E. That's what we just solved. E to the 5, 2.5, down some. So the answer to this was this. So we've got E to the negative 5 from 2.5 equals 1.58 times 10 to the negative 23. That gets us down to a very simple step. What we have left is K equals A of course I erased the rate constant. And K was 6.1. Negative 8. If these calculators do it, you can put the powers of 10 in there. But I would divide both sides by this. So it's 6.1 times 10 to the negative 8 and 1.58 times 10 to the negative 23 equals A. I would just go 6.1 divided by 1.58. 6. I have 9.63, but because of the 6.1, I'm going to stop there. And then to solve the negative 8 and negative 23. I'm going to move this up to the top. That changes the sign. So 10 to the negative 8 times 10 to the 23, and you get 10 to the 15. So the answer here is times 10 to the 15. And it's per second. So I'll do one like that on the test. I did next. I won't make you graph on the test. But if you're looking at the PowerPoint, you see the next page has a graph on it. This is into chapter 62.
For column 58, is there just a way to plug it into like K equals A activation energy over R2? That just
You mean solve for A somehow?
yeah.
Like it would be that if you solve for A. But still you're going to start by solving all of this and then using your calculator, the exponential function, to find out what that is, and then dividing K by that. So it's just dividing both sides by this. You good with that? All I can say is practice it.
So you wouldn't give us that on the test?
Huh?
You Did you give us that on the test, like A equals or B?
Well, I'll give you this on the test, but that's a very simple step if you're solving for A. Did it lose you somehow? It's just that algebraic step, divide both sides by the same thing. You okay with it?
Yeah.
All right. I'm definitely giving you this on the test. I'm giving you everything that's on here on the test. There could be variations of this. I mean, there's 1, 2, 3, 4 themes here. I could give you 3 out of 4 themes and make you solve for the 4th. Although I would put it on D2L under quizzes if I was going to do more variation. But this one gave you energy, temperature, and K, and you solve for A. But you could be given A, energy, and temperature, and solve for K. R is a constant, so that's never going to change. 62, we're going to use this variation. That 1 over T. So for this first method, and I'm probably not going to have you do this on a test, I just want you to realize you have to use this method if you're using experimental data and it doesn't line up perfectly in a straight line. I'll sketch the graph I got. This is what they give us. They give us temperature and K. That's the data they give us. And we're being asked to find what is the energy of activation. That's what we're looking for 62. So they give us this. I graphed it and got a nice perfect straight line. Oh, wait a minute. This isn't what I graphed. What I need to graph is, if this is y, then I need to take the natural log of this. And if this is m and this is x, I need 1 over t for the x. And that's what I grabbed. If I did that, I got the data there. If you got the spreadsheet, it's, maybe I won't write it. But not the spreadsheet. You guys looking at the PowerPoint? So you see this little box right here. I just copied that over from Excel, and that's these values. So what I did was I made one more little grid of 1 over t, natural log of k, this is what they gave us. And I went ahead and calculated these values. Calculated these. They're there in the PowerPoint. And that's what I graphed. And this was my x value, that's here. This is my y value, so I've got, what I've really got graphed here is natural log of k and 1 over t. And that's what's supposed to make a straight line. All right. I was going to say, oh, they all line up. And I told Excel to give me this. So Excel has given me the equation of this line that fits straight through here. It's a negative. I also went ahead and said, give me the R value, the R squared value, and it gave me a 1. That 1 is what really tells me that this lines up perfectly. But if it was 0.999 something or 0.998, you could probably still rely on this slope to move forward. But since that's supposed to be the slope, according to Excel, and that's the slope, I just take that value, I go equals negative E A over R, this, and now I can solve for activation energy like that. But typically you want to do this when you have data that's a little off and your R square value is a little off from 1, but you're like, okay, I'm getting an estimate from my data, that's all I got here. And then you do it that way. If you solve like that, I've got down in the bottom left corner how I solved it. But you're going to go times R equals negative EA. You with me? Algebra?
What do you plug in for natural log of A all the way to the right on the top equation?
For this?
Yes.
Oh, A is just a general formula. In this case, we're talking about, I have to read the equation, but HI. In this case, it's HI. And that's concentration. So for this case, if I made this specific for this case, not general, HI, and this is natural log, yeah, that's right. That's the initial concentration of HI.
So you can't like solve for that, you just put in it.
This we don't even really pay attention to. That's the y-intercept. So if I went all the way up here, that's the value right here. This is natural log of HI. Notice this is time, and this is 0 right at the very beginning. So that's the initial concentration. That's why I put a 0 there. But we're kind of ignoring that. We don't need it for anything we're doing here. I'll consider whether I'll ask you a question. What was the initial concentration of the HI? Because you could solve that if I gave you the activation energy for this reaction and the K for this reaction. You could solve for it. And the temperature I did, you could solve for it. But I don't have any questions on that yet. So this algebra, are you with me here? This was the slope. I set it equal here. I multiply both sides by R. All right, so then, and the R is, and I'm leaving the units out because I know that it's going to be, I know what the units are for these. So I'm solving for energy of activation. I know it's going to be joules per mole. Anyway, I've probably kept too many digits, but by the time I got that for joules per mole, and then I looked at the values I'm using. I started with 3 significant figures, 3 significant figures. So I'm just going to go back to 3 here. So 180 joules per mole is what we get. And you can now go 180 kilojoules per mole.
Can you solve it with the data in the chart instead of using y? Like if I took the...
Yeah, that's the next method I'm going to do. That's probably what I'll have you do on the test. I just don't know if they'll mess you up on an ACS test. They'll show you some data that's not perfect and a line through it, an equation. They might do that, and then you'll want to use that instead of this data. But yeah, so I call that method 1 here. But really method 2 is the more important. I just did this part to sort of paint the concept again. The other equation, so this was method 1 on my, that's method 1 on my PowerPoint. If I want to use method 2, I still need some of this. But let me get all of this out of the way. Let's say it's method 2 on the next page. If you've got a graph with a slope on it, it's a little quicker. But if you don't have a graph and you don't have any way of knowing, you've got these 4 data points. What you want to do is use the full gamut that this runs. You want to use the first data point and the last data point. Again, I'm not using these, I'm using these, the 1 over t and the log natural k, natural log k. And now the equation you want to use is this next equation. It solves for energy of activation directly. Negative r natural log k2, natural log k1. I guess I should do this. I didn't do it on there, but 1 over t2 minus 1 over t1. So it's that equation. So I'm picking data from here, not up here. And if I plug them in, method 2. So you see my data there. So once I plug the data in, it doesn't matter which one you call 1 and 2. So whichever, typically you would call the first one 1 and the last one 2, but it really doesn't matter which one it is, as long as you stay consistent here. These are paired, these are ordered pairs, and these two are ordered pairs. So we've got these two together, and these two together. These two together, and these two together. 2 and 2, 1 and 1. As long as you do it like that, you'll be okay. But that only has to do with the negative sign, really. I guess it won't fill in all my data, but you see it on the PowerPoint for number 62. And I calculated, I came out to the same thing. I've got EA. And then I went 180,000. This was joules per mole. And then I ended on significant figures, like whether you put a period here or not, whether you put the decimal here or not. Because of the way I'll do the test, it's gonna. I'm not gonna do stuff like 180 dot and 180 without a dot. I'm not gonna play games with stuff like that. Truthfully, I didn't go over the rules for significant figures with natural logs because your book didn't. I don't think it did. But that's why I keep keeping a little bit of extra digits because it saves you some round off error. All right. So next. Method 2, so here. All right. This is one of the check your learning things in the chapter. I didn't write down which one it is. It's the only check you're learning from the Arrhenius chapter. I don't remember which exercise it is. So I'll go through this one too. This is probably the way I'll give you these on the test. I don't have questions like this on D2L yet, but I plan to. But this one, the information in this one says, rate constant for decomposition, blah, 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 is, so it's saying K equals, and they give us liters, mole, second. At T equals, and then they also give us K equals 7.39 and T equals 700K. So that's just like those two data points. We've only got two data points. There's only one way to do this. It'll come out the same whether we, if we graph this, we're going to get the exactly same slope as the way we're calculating it. But don't worry about that. The calculation we're using here is again calculate the activation energy. So we're using one and two. I'll be consistent just because that's the way I listed it on there. 1 over T2 minus 1 over T1. Okay, so this is our data. Why don't I do this? There's no powers of 10. But what I need is, truthfully, to keep things straight, I probably should have put temperature on the left side. Oh, that only matters when you're graphing it, really, for Excel. I need natural log of K and 1 over T. So let's do that. Scientific. So 1.66. I know it's here. Keep 5068. E to this. Whatever, I'll keep that. It might not be exact. 7.39. So be sure you know how to do this on calculators in here. And now the 1 over t's. 1 divided by 650. 650. I'm going to assume that's 3 significant figures, even though there's not a period here. 001538. And then 1 divided by 700. And now we'll just apply that formula. Negative 8.314. And then natural log of K. Let's call this 2 and 1 just so I can stay consistent. But it doesn't matter if I call this 2 and this one 1 and fill them in, it'd still work out fine. But just because that's the way the formula is, I'll stay consistent. So 0.568 minus 2.0001 over. Oh, I just did 1 and then 2. It's not going to matter. As long as I'm consistent. What am I thinking here? K1, K2. I did K1 and K2. Now I need 1538. All right, 0.5068 minus 2.0001. 001538. Four after the decimal, 4 after the decimal. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, I guess that's right. You should always end up with a negative in here to cancel this negative, because the energy of activation is always positive. Okay. What do I get here? divided by 0.0001. And that's negative. And now that times 8.314. Three significant figures, that's right. So now I get EA equals. Keeping 3, I guess I get to 114 here. Wouldn't the spreadsheet show? Oh. Why would I get 2 significant figures? Whatever. This is one that the book did, and they kept 2 significant figures, so they did this. Just to stay consistent with what they did on the book, I'll go EA equals 1, 2, 3, 4, 1, 2, 3, 4. They did that, and that's joules per mole. And then they went 1.1 times 10 to the 5 joules per mole. And then they ended on and that's still 2 significant figures. You guys okay with that? If I put any one of these as the answer to it on the test, could you recognize it? Whether I did it in joules or kilojoules or joules times 10 to the 5. You okay with it? You're not okay with it. Well, take a look at it, make sure you're comfortable with it. This is one more of those. And this is one more of those. All right, why don't I just leave the next 2 on the PowerPoint is end of chapter 59, 63. So that's just like this one that I just solved. Those are. Pay attention to the units. 59. It looks like they give you Kelvin in both places. Pay attention to whether they put it in degree C. And let's look at I was considering going to the next section this morning, but I'd rather save that reaction mechanisms. But let's look at these problems that I just put on U2I. Quizzes. The rate law, the statement of the rate law, you'll see what I mean. I think these are easy. Look at question number 1. And let's consider these A, B, C, D, and E. So what's the answer here? First order order in the long thing, zero order in H2O. You say B?
Oh wait, mine is different than yours on my phone.
Oh, yeah, it randomizes the choices, so just look at what I've got up
Oh,
here.
see, sorry.
Okay, yeah. It's K, and then it's just the concentration without a unit. That's not going to help for the video, is it? All right, good. Well, whoever's watching the video can go practice these. How about this one?
Oh, wait.
They're both first order, so it's the last. Notice putting a 1 here is pointless. You don't really need to put a 1 there if it's 1, so it's really going to look like this if it's first order. It won't have the power there. Let's see. Second order in NO2 and 0 order, it's this one. I got a few of these. Y'all can practice those. I'll add more if I have time, but I need to get the other types of questions up there. Okay, what I have for this one, the integrated rate law. Give the data below. You don't really need to look at this data. Do you have your integrated rate law sheet with you? But what are you looking for here?
Linear.
Linear. And which one is linear? One on the right. And what's on the axis there?
1/2.
It's 3, 1/3. It's 1 over this in reactant. And which order does that go with? What is it? It's second. I have these in order. I won't necessarily put them in order on the test. But this is what first order would be, just the concentration. 0 order would be just the concentration. First order is the natural log of the concentration. And second order is 1 over. So you're looking at that axis for the integrated rate law. Oh, right, okay. This one is saying, what is the value of the rate constant? You've already decided what will decide the second order, and you need to know that looking at this data. So I might just give you a question like this, and I'm not asking you for the order, I'm asking one step beyond that. What is the rate constant? If it's second order, what I have on here for the rate laws for second order, this one is timed 2 times. One over concentration density. Second order. And you can solve this by, you're essentially finding the slope here. But what you're going to do to find the slope, put it this way, the slope I'm missing the negative. No, not this one. Slope equals K here. And you find the slope just by doing rise over run. So now you look at the data. Why is this? So I've got all three. What I've got graphed there, I've got time over here on the left. In time versus concentration of O3, if I just highlighted these first two columns and said graph it, that's what I've got here on the left. If I highlighted time and then natural log of O3, that's what I've got in the middle. And then the one on the right is time versus 1 over O3. So we're looking over here, and the 1 over O3. So we're using the time column and the 1 over concentration O3 column. So I'm going to use 0 at 17,000. 17,000, and I'm going to use 0.0001 minus 10. That'll give me the slope. I did these in a spreadsheet. Hopefully I did it right. This is, of course, negative. I'm just tempted to keep all of this. And this is going to be 0 minus 1,700. 17,000. So what do we get? 99999. Divided by 17. No, I did that wrong.
Yeah,
I was using
the
the
1 over
0 to 1,700 and 10,000 in. This is why I don't do these in front of you guys anymore. This is why I do them in a spreadsheet. All right, tell me what it is.
0 minus 1,700. And then we're using the 1 over O3, right?
Yeah, the far right column. So what goes opposite 0?
It's 1 0 0 0 0 0.
5 zeros?
Yes.
All right, minus, and then what's that other number?
952 380 .952.
Probably don't have to use all those digits, probably just the first 3 or 4 would be fine. But since I do it in a spreadsheet, I don't know, truncate the numbers. 3, 4, 5. Minus 952 380 952. Let's just keep. Whatever. Let's keep all of it. You should come out positive here for the second order. This will be negative, or this will be negative for the other two, because they have a negative sign here. But for the second order, you should have negative, negative, or positive, positive, but this should come out positive. 852 380. 17,000. I've got 50.1, is that there? Good. You see the 1.88? I started to put the trick answer in there as if you used the wrong column, and then I thought that's a little too cruel. Because then you'll think you have the right answer after all you got, but you used the wrong column. And you see how I can be funny. I try to go too fast. But anyway, you got one thing left to discern, though. Which one of these is it?
Is it the bottom one?
It's this one because it's second order, and that's the units per second. if you didn't have those top two problems, you would have first go, okay, this is second order, and then you'd have to calculate K, which is 50.1, and then you can calculate the half-life. And I think the way these quizzes are when they're presented to you, you can scroll up and see your answer up here. On a test, I won't make it a compound answer like that. I'll make up a whole new thing and then give you the K. But I just, because this worked in sequence, I put it together. But again, you're going to look at your cheat sheet, and it tells you how to calculate the half-life. And that gives you T1 half 1 over K A naught. In this case, A naught is 0.3. Initial concentration of 0.3. You just look up at the top, that's the 10 with the 5 zeros. And the K was 50.1. Denominator, get of course. One divided by 501. Yes, because I did this in Excel, I thought I fixed these, but we don't have so many significant digits everywhere. Yeah, I fixed these last ones, but let's just keep 3. I guess I need to fix this, because that's too many. Over here on the right, that's way too many significant figures. So it's a tiny, tiny fraction. Something wrong. What did I do wrong? Got this in seconds. 1.996 seconds. What did I do wrong? I was real careful doing this yesterday. This was second order, right? What did I do wrong? Oh, I used this, okay. This is a good lesson for y'all. I keep doing this myself. So yeah, that's the right formula. And if I asked you, what does that equal? Because we have to go T1 half equals 1 over K concentration of that, 0.3. So we need to know that concentration. Look at this data and tell me where that is. The initial concentration at time equals 0.
Is that the first column?
Yes, that's what I did wrong. You're tempted to keep looking here when you do the half-life, but when you do the half-life, you need the initial concentration. What I needed was this. You see what I'm saying? That's where I messed up. So it's 50.1 times 0.00001. So now it's 0.0501. One over 1 divided by by 0.0000501. And I probably kept too many digits, but 996 is what I put. That many seconds. Because this is a time. So it's not seconds to the negative 1. Let me point this out. I don't have my spreadsheet. You can look as a double check for that. I need my spreadsheet that has a blow up of this, and I didn't bring it. But this shows time in seconds, and it shows the concentration here. All right. If you look at wherever 19996 is on this axis and over here, it should be about 1/2 of the initial concentration. This one, if I told you you're not allowed to calculate it, and you took a stab at what the T1/2 is, do you remember what T1/2 actually means? It's the half-life. That's the time it takes for half of it to disappear. So this is the concentration here. And if I lined up these digits, this right here, the 498, if that said 500, that would be exactly half of the one just above it. You see what I'm saying? It's just because of the zeros and the powers. You can't line it up. But the second entry here, for here, is about half of the first entry. So really, if you wanted to estimate, you would say it's going to be at about 2,000 seconds. But we did the calculation and we got this. But as a double check, when you do half-life calculations, be aware of what it means, the half-life. And then you can see if you did something wrong. I knew I did something wrong because the answer wasn't here. But the answer was, the power was way off. All right, I've got 3 of these in here. Show it to you this way. I've got decomposition of ozone, the one we just did, decomposition of O2, and then just sort of a made up decomposition of CE. So each one of them has 3 questions under it, and it's those same 3 questions. You probably should have more example disease, but what I did is there's an order 2, there's an order 1, and there's an order 0. So I am going to just stop there for the day. I don't want to go on to reaction mechanisms until I sort of short up everything. I think we're good on integrated rate laws. If you're okay with the Arrhenius equation, what's in the PowerPoint, then you're probably good. I do need to go back. I think I should go over rate law a little bit more. So it's rate law, integrated rate law, and Arrhenius. I'll go back to rate law a little bit Monday, and if I feel good about it, then we'll go on to the next section. I don't know if I'll get to equilibrium stuff the next chapter. All right, y'all have a good weekend.